great pleasure to introduce Sami Rifai and welcome him back to the country at long last. So Sami has been working at the ARC Centre for Climate Extremes over at UNSW for the past few years, but he's been doing it remotely from the US. So we're very pleased to finally see him back in the country. His work focuses on looking at how Australian and tropical forest ecosystems are affected by climate, CO2 and disturbance. And he's particularly looking at remotely sensed approaches with statistical modeling to look at ecosystem processes. And so today he's going to be talking about recovery from fires. So thanks, Sami. Look forward to it.
Great, thank you for the introduction. Let's see. Okay, so this is work done in conjunction, in collaboration with Martin DeCow, Rachel Gallagher, Lucas Cernisak at JCU, Patrick Muir, formerly at ANU and now back in Edinburgh, and Andy Pittman, our director at CLEX. So I'm not really framing this talk around trying to predict recovery from of forests from fire across all types of forests, because there's just vastly different timescales at work. In boreal forests, it's decadal, multi-decadal to centennial scale. And under different disturbance regimes, even in wet tropical forests, the time to recover can actually span decades because species are maladapted to fire. But within Southeast Australia, recovery can occur perhaps most frequently on the subdecadal scale. And this is despite exceptionally high interannual rainfall variability, relatively or comparatively phosphorus poor soils. But it can do so because of adaptation, really this capacity to resprout. So my motivating questions in this talk are, one, what remote sensing derived metrics can we use that would be suitable for tracking recovery? And this is really dependent upon how we can operationally define recovery, and especially when recovery is really just coming from a remotely sensed signal. Two, conditional upon this definition of recovery, how variable is the time to recover across Southeast Australian forests spatially and temporally? And then finally, what drives this variability to recover across these forests? So first off, this is our region of interest, mostly focusing on areas that were affected by the 2019-2020 mega fires. So that's mostly, coastal-ish New South Wales and Victoria. And in this work, I'm really tracking fire through one specific product. This is NASA's burned area product, MCD64. It has about a 20-year time series. And then I'm only going to focus on eucalyptus-dominated ecosystems as designated by the National Vegetation Information System. So from the most xeric end, these eucalypt open woodlands, where precip is far less than potential evapotranspiration, to the middle end, these maybe eucalypt open forests, which are also somewhat flammable and of intermediate aridity, to the wet forests, which are much less flammable and burn probably, we think, less frequently, but generally have much greater precipitation than potential evapotranspiration. So the last 20 years of bushfire in Southeast Australia have been super wild. The mega fires from 2019-2020 essentially burned about twice as much as the previous worst year in the record around 2003. Not surprisingly, the total burned area is negatively correlated with precipitation and positively correlated with vapor pressure deficit. And what's really striking, I think, about the most recent fires is that the VPD reached levels unseen by the Bureau of Meteorology's sensor network, essentially. So the VPD, the vapor pressure deficit during these most recent fires was record-setting, essentially. So I'm going to go through essentially 6 potential metrics to track recovery from fire, essentially. So starting with the most classic and probably widely used metric, the normalized difference vegetation index. This is just calculated from the red and near infrared wavelengths. And then since then, this is since the introduction of NDVI, there's been almost an arms race to come up with better variants of it. Essentially, variants that can better track things like gross primary productivity. And so the kernel normalized difference vegetation index is one of the newest variants of this, and it was designed to essentially help overcome some of the saturation issues that NDVI encounters as the leaf area increases. And supposedly, it's a better proxy of gross primary productivity than other vegetation indices. Another index, which is actually more used in boreal systems, is the chlorophyll carotenoid index. And so this is being claimed to also be a pretty good proxy of gross primary productivity in evergreen conifers. And this is an area where NDVI, for example, really fails because the leaf area is not changing so much seasonally within these boreal forests. So I had it in my mind that I thought, why not try this this metric from left field to see if it works. The fourth surface reflectance based index I'm going to use is really a modeled product. It's modeled leaf area index that's estimated through a radiative transfer model, and it's again mostly just using the red and near infrared wavelengths, but this is conditional upon the vegetation structure. So if the vegetation has been classified as grass or evergreen tree, it would have a different LAI depending on its on the reflectance of the red and near infrared wavelengths. So this product is not perfect. There have been at least a couple papers sort of poking holes in it in earlier versions of it, but it is fairly useful, and it's pretty widely used across essentially global change ecology. Two other indices, tree cover. This is the Modus Vegetation Continuous Fields product. This is estimated through a decision tree algorithm. So this is essentially taking all the surface reflectance wavelengths and generating this annual estimate of tree cover. And then finally, a non-spectral metric. This is the difference between canopy temperature, or actually the Modus land surface temperature, which I'm calling TC, temperature of canopy, minus air temperature. And you can use this as a proxy of the canopy evaporation potential. So this is really far from an exhaustive list, but I think it's already kind of overwhelming. Next, I need to bring you through two frameworks about how to define recovery. So the first is a moving window estimate. And the advantage here is that it's a pretty simple approach. There's really no statistical assumptions. And if we make the window wide enough, it can counteract the effects of seasonal phenology. So if there's pulses of grass in one season, if we make the window wide enough, we can smooth over it. But this is arguably an arbitrary decision, this window size. But also we need to work on what is an appropriate threshold. So is the mean annual LAI really an appropriate threshold, especially if co-occurring changes in hydroclimate are occurring? You might not really expect a forest to recover to an LAI from a wetter time if the climate is ratifying. And then finally, I want to preface this and say that I'm not claiming that this is going to be a very good proxy of recovering biomass or recovering diversity. So in gray here, what I've plotted these points are the deseasonalized LAI estimates for a given pixel. It's pretty noisy. There's lots of transient peaks. First step in sort of removing some of this transient peaks is to just run it through a smoothing filter, essentially. So this helps remove some of that signal. And then to essentially, oh, yeah, sorry, I should have advanced the slide. And then we can apply this moving window metric. So if I set the moving window to be 12 months, it's not going to be able to estimate recovery for at least 12 months. So as if this is the time of the fire, then it's 12 months coming down, and then it's beginning its journey back upwards. Then the next part is that if we define recovery at the mean annual level, then a lot of forests are not ever, probably not going to recover in our lifetimes if some of these decadal changes in aridity are going to continue. So, but if we widen this threshold just a bit by even a quarter standard deviation, and essentially 97% of the burned area, at least in the record so far, will recover within a quarter standard deviation within 6 years, essentially. So this method is pretty nice. There's very few assumptions, but it can only estimate the time to recover that's longer than 1 year, and it doesn't really give us any information on the rate of recovery. But it's a good metric perhaps to, or perhaps it's a good approach to weed out which vegetation indices are going to serve our purpose here. So what I've plotted here is for each fire year, the fraction of recovered pixels through time. And the blue dots represent when 95% of the pixels have recovered. So just sort of eyeballing this over, more or less these things look fairly comparable. You might see that this land skin temperature minus air temperature seems to recover a bit sooner than most of the other metrics. But this is perhaps not a good way to visualize it. Another way to visualize it is just to look at the cumulative distribution function of the fraction of recovered pixels through time. And this, I think, reveals some big inconsistencies across some of these vegetation indices. So, for example, the chlorophyll carotenoid index here in red was the fastest to recover index throughout the early 2000s. But as time went on, it became the slowest to recover index. So whatever this is capturing is really changing on a multi-decadal timescale. And it just seemed too inconsistent, really, to use for this analysis. The MODIS tree cover product is kind of nice, but unfortunately at an annual time step, it really limits our comparison, and it would drastically limit our resolution of predicting the time to recover. Where the MODIS LAI, so in this light green color, and the KN-DVI in this yellowish color, these track each other pretty closely, and they're consistently in the middle of the pack in terms of the rank order of recovery. And then finally, this non-optical difference from canopy, from land skin temperature and air temperature roughly tracks the LAI and KN-DVI, and then it sort of recovers much faster. So moving forward, I'm really just going to focus the rest of this talk on the LAI metric. One, because it's interannual consistency across fire years, but two, just because it's biophysically interpretable, and that I think can help. So my second approach here is more for quantifying time to recover, is more statistical, and it's just using logistic growth function in the time series of LAI. And so here we can fit each time series to this function where L at time t is the leaf area, K is our carrying capacity, so we could set this to something like the mean annual LAI. L0 would be the leaf area right after the disturbance, so the minimum leaf area, and R would be our growth rate. And I think this really has some advantages. One, because it can characterize nonlinear recovery, so this fits the time series much better than, say, a linear model. And two, it can estimate the rate of recovery, this R parameter. And with these in hand, we don't necessarily have to just estimate recovery at the 1 year time span or longer. This can estimate shorter time spans, like sub-annual recovery for forests that are not that burnt. The main disadvantages here is that it can be tricky to fit sometimes. So if a time series is very non-monotonic, going up and then drastically going down, it can fail to fit. So we lose about 20% of the pixel locations because it fails to fit. And so what this would look like is taking this time series. So in light gray, this is essentially the smooth data after the Whittaker filter. And then I just fit this logistic function to the data. And then because I've specified a quarter standard deviation beneath mean annual LAI is my recovery threshold. This is the point of recovery. Yeah, and so it provides a pretty straightforward way to statistically estimate recovery while also extracting information about the rate of recovery. And so these two methods compare pretty favorably. Here on the x-axis is the logistic function estimate of time to recover. Y-axis is the moving window estimate. They're highly correlated, 0.88. And as we would expect, the moving window estimate is positively biased. It's always longer because it can only estimate recovery at the 1 year or longer time scale. So, okay, moving into one of our first questions. So how spatially variable is the time to recover? Here I've plotted 3 fairly large burns that occurred in the last 20 years in Mugham State Forest, in these very large fire in 2003 near Canberra, and the Kilmore East fires, which were really catastrophic, I believe. So on these panels here, I've plotted the 95% shaded interval of different of the recovery trajectories of all these pixels within these burns. So within any fire, within any one of these large burns, there could be fast recovering pixels like this purple one here that within the time scale of 1 year essentially has recovered, to these much more slow undulating recoveries that more slowly approach our threshold. A different way to view this, perhaps an easier way to view this, is to just look at these fires as individuals. So what I've plotted here, this is the moving window estimate of the 10 largest continuous fire locations. And so there is spatial structure to these. However, each fire really has a pretty wide distribution in the time to recover. And in part, this is because each burn, or each cohesive burn area also encaptures a pretty wide range of burn severity. Okay. But the size of the burn itself really does not seem to have much predictive power in sort of trying to predict the time to recover. With respect to how temporally variable the time to recover is, so this can vary by about a factor of 4, where say the recovery time of pixels of burnt pixel locations in 2005 was about 4 times longer than it was in 2010. And most likely this is driven by rainfall, essentially. So as the progression of the Millennium Drought went on, the time scale, this decelerated the time scale to recover. So here, during the peak, during the worst periods of the Millennium Drought, is when we see our longest periods of the time to recover. However, the 2010-2011 La Nina event, which brought deluges of rainfall, dramatically reduced the time to recover. And that actually lingered for probably at least another fire season or more. You can also see the effect where the fires that occurred following the La Nina event generally produced much less reduction of LAI than did fires at the beginning of the Millennium Drought or the most recent mega fires, which caused the largest drops in modeled LAI. So coming to this, the bigger question of what is driving this time to recover. Here I plotted the time to recover against 2 different metrics of burn severity. So on the left is this moving window estimate. So against burn severity, where I'm essentially relating this to the fraction of LAI consumed by the fire. So this is just 1 minus the LAI post-fire divided by the mean annual LAI. So if it's 1, it's complete consumption, hypothetically. And so this time to recover mostly increases and to a point at about 0.75 and then comes back down. In contrast, the statistically estimated time to recover and statistically estimated burn severity give us essentially the same pattern. So we both have this, both methods are indicating that there's this nonlinear peak in the time to recover around 75% burn consumption. So I think this is really odd, actually, that essentially the most burned pixels do not seem to have the longest time to recover. So what I think this is that the burn severity seems to be related to the post-fire growth rate. So what I've plotted here is essentially all the pixels that were fit with the logistic function estimate. So on the x-axis here is another estimate of the burn severity, and the y-axis is the recovery rate. And so the recovery rate is a bit higher when the burn severity is very low. It's at its highest when the burn severity is at its highest, essentially. And so using this trend here, this is actually just a generalized additive model trend, taking this same relationship and then plotting it against how this would affect the time to recover if we knew the burn severity, let's say a small reduction in burn area to a complete reduction in burn area, and then just using the logistic function again to estimate how long it would take to recover given this the gradient of consumption. And here, what we see is that this black edge here, where pixels might be complete, or LAI might be completely consumed, would recover essentially in half the time as a forest at the minimum of the recovery rate. So at, say, a consumption of about 75%. So this is, I think, really a curious response, and I don't know why. I can only speculate. Maybe it has to do with the release of soil nitrogen and phosphorus, or does this have to do with just annihilation of understory competing vegetation? Or could there be differences in sort of species levels, non-structural carbohydrate pools, or could this be doing something to cue the allocation of those non-structural carbohydrate pools to growth after the fire? So this got me on this path of trying to relate what we were seeing from the satellite data to species level differences. But there's really no off-the-shelf, at least to my knowledge, there's no off-the-shelf species distribution model to assign the most likely species to each burn pixel location. However, there is the Atlas of Living Australia, which is a terrific resource, which has compiled the species collection records across all of Australia. And so for this region, what I did was, with Rachel Gallagher, was to take all of the observations that occurred from 1930 onwards that had at least 80 observations, generating about more than 60,000 observations, and then to use this to construct species distribution models. So this was where our response variable was one of 108 potential different species that had from the species records that Rachel and students had really cleaned up, I believe. And then to just put all the possible predictors that we could regarding mean annual climate, seasonal differences in climate, terrain aspects, elevation, slope, etc., soil edaphic properties, and then vegetation characteristics into a machine learning model. This one is a XGBoost model. This is a variant of decision trees, essentially, with a multinomial response to generate this potential probability of occurrence. So this is not really I know this is not the actual species that's occurring in any one pixel, but this model, trained model, has a 42% accuracy on withheld samples. So data not used in training has the model can correctly pick the species 42% of the time, which, considering that there's 109 potential species it could pick, I think 42% is pretty good. But these pixels are, of course, pretty broad. They're 500 by 500 meters, so any pixel is really going to have an assemblage of tree species, most likely. So I'm really just calling these the species distributions. But now that I have these species distributions and these burn histories and these estimates of the time to recover, perhaps we can start examining species level differences in this time to recover. So that's just what I did here. I just plotted the box plots of these 106 species that had experienced fire in the record using this moving window time to recover estimate. And I plotted these color bars along the gradient of potential evapotranspiration, where when it's the more brighter colored, it's has much higher PET, and when it's darker blue, it's lower PET. So you'll see why that essentially PET is increasing with the longer time to recover. So the shortest recovering species or species distributions, such as Eucalyptus minoides, which is recovering essentially all within a 2-year time span, is really existing at a much higher range of the PET spectrum, in contrast to Eucalyptus mitchelliana, which is far. Sorry, this window is in the way, but it's really pushing the upper boundary of like 6+ years beyond to recover. And now that we have species distributions, we can perhaps start connecting this to functional traits like the fire response traits with density, specifically failure. So, and this was really only made possible because of the Oz Traits database, which was recently published by Daniel Foster and Rachel Gallagher and hundreds of other contributors to this. And so this is not a very definitive analysis. Consider this just a first stab at trying to connect a remotely sensed derived response to functional traits by way of a species distribution model. So I know this is very indirect and there's plenty of room for error, but it does sort of indicate that there might be very small responses, depending upon the method of estimation, where wood density the growth rate, post-fire growth rate seems to increase with wood density, and it seems to increase with specific leaf area. And the post-fire growth rate is lower in regions where the species distribution is dominated by fire-killed species, and it's higher in areas where the distribution is dominated by species that sprout. Note that these are huge differences, but I think there's potential in this approach of connecting remotely sensed data with field observations and by way of species distribution models to potentially learn something at scale about species level or species distribution level responses. So next, I'll bring up this more to get it out of the way. So this is another. I submitted this work before, and one of the reviewers brought up that what about fire history? And it's true. I've really only focused this analysis on pixels that had burned once in the record before the Black Summer fires. So what I did to address this point was to get the New South Wales and the Victoria shapefiles of previous burn area in the 20th century, really more focused. Most of the records are from 1950 onwards, and try to relate this to the time since the last fire to the growth rate. And my very cautious interpretation here is that there might be a very small but positive effect on the post-fire LAI recovery rate that dissipates within 10 years. But I'm really cautious about this because the vast majority of these pixels were not tagged as having burned in these databases. And there's a lot of uncertainty about the older fires in these databases. And this could be done much more rigorously by using the Landsat records and the much longer Landsat record in combination with the more recent MODIS records. Okay, so coming to the crux of this talk, what drives this time to recover? So overall, the burn severity is fairly related, not surprisingly. The post-fire growth rate is the most related, so a higher growth rate, of course, brings you to a faster time to recover. But surprisingly, the mean annual LAI is almost unrelated to the time to recover. And so what I'm going to do to show you some of the effects that I think are structuring burn severity in the post-fire growth rate and the overall time to recover is to use generalized additive models as sort of a tool for exploratory inference, because these are very flexible. They can characterize nonlinear effects. They're visually interpretable, and they have reasonable predictive performance as well. So in the first model here, I'm just focusing on burn severity. So in the effect here, this is the contribution to burn severity. So if the effect is high, on the x-axis, the variable on the x-axis is contributing to greater burn severity, more burnt. And if it's low, then it's less burnt. Okay, so and note that the y-axes on these plots are different. So for the first plot, this is the pre-fire LAI anomaly. So this is essentially how much leaf area senesced in the 3-month period leading up to the fire. And perhaps not surprisingly, if forests lost more of their LAI right before the fire, the burn severity was greater. That I don't think is surprising. There's more fuel. Perhaps what is surprising is that forests that overshot before a fire, that is to say that a forest that had an LAI notably greater than, say, its mean annual LAI, but then maybe lost its LAI, perhaps leading up to the fire. These forests also, these burn severities were also greater in forests that had anomalously high LAI preceding the fire. And then finally, precipitation, to no one's surprise, that if it was fairly wet leading up to the fire, that the fire is likely going to be much less severe. So if the seasonal precip was higher than expected, the fire is likely less severe. Next, this is a model with 6 terms focusing on the post-fire LAI recovery rate. And so here we have 2 types of drivers. We have these static drivers, which I'm calling, so mean annual PET and P to PET. This are otherwise known as the moisture index. So the post-fire recovery rate does seem to increase with PET up to a point at which then it declines. And likely this is best interpreted in conjunction with the moisture index. So if a forest is in a location where it has relatively high PET, but it ranks moisture essentially higher on the P to PET ratio, then the recovery rate is generally faster. But if it has a really high PET and it's low on the moisture index, so much greater PET than precip, then the recovery rate is generally going to be lower. So those are our 2 static drivers. Our dynamic drivers, again, come back to the pre-fire state of LAI. So how much trees or forests seem to senesce right before the fire. So if they senesced a lot, essentially, surprisingly, the recovery rate, the post-fire recovery rate seems to be faster. But I do acknowledge that this could be somewhat conflated with the burn severity again. So where as the burn severity increases, the recovery rate is also much greater. But ostensibly, these 2 things are happening in conjunction. So if there is a pre-fire drop in the LAI, this is contributing to fuel, contributing to greater burn severity. But overall, it's still, again, the models are suggesting that the post-fire recovery rate is greater in forests that burned more severely. Next, the last shoot, the time of the fire seems to be quite important. So early season burns have faster growth rates than late season burns. But then also the post-fire precipitation is really structuring a massive chunk of this. So if it's wet beyond, if it's wet in the 1 year following the fire, the recovery rate is much higher, essentially. And finally, this is just a suggested model of the overall time to recover. So again, we see this peaked response where the burn severity the time to recover seems to be greatest at these fairly high to intermediate levels of burn severity, but it comes back down. And then we have the pre-fire precipitation, which perhaps surprisingly suggests that if a forest was in drought preceding the burn, its post-fire overall time to recovery is actually going to be reduced. So it'll have a shorter time to recover. And then the post-fire precip again. So if it's wet after the fire, then the time to recover is also shorter. But then I think the most surprising aspect here, again, comes back to canopy overshoot. So if a forest had overshot its mean annual LAI, it seems to have a longer time to recover than forests that had not overshot their LAI in the year preceding the fire. So, but again, this is just sort of meant to be suggestive of the underlying causes of time to recover. This model has a reasonably decent R-squared of 0.3 and a mean annual or mean absolute error of about 300 days. But we can do much better than this. And then again, it comes back to machine learning techniques. So this time, gradient boosting, akin to what I used in the species distribution model. But this time, I can feed it the normalized burn ratio as a metric of burn severity with essentially the same predictors of mean annual climate, seasonal climate, terrain, and soil characteristics, and potentially also the species distribution models. And from this, we can estimate a continuous predicted time to recover. But we'll note that ultimately, I removed the spatial information from this to maintain some generalizability of the model so that it's not just sort of predicting, that it's not overly biased by places that had burned in the past. And part of this meant that essentially adding the species distribution models to this didn't really help because within the species distributions was encoded, essentially the spatial coordinates are encoded in the species distribution. So that didn't really help the overall prediction. But the overall prediction did seem pretty good. So this is an R-squared of almost 0.7 out of sample. So this is the predictive capacity of the model on data that was not used to train the model, on a solid quarter of the data that was withheld from the training process. And so we can get to essentially an error rate of only about 177 days. So I think there's a lot of potential to just using sort of off-the-shelf machine learning models with landscape data to predict the time to recover. But it will be important to test this prediction in the years coming. So essentially in the next few years, you should be able to predict what fraction of the landscape actually did recover and was this version of the model correct. And next, what this model essentially predicted is that despite the burn severity being dramatically higher during the Black Summer fires than preceding years, the overall time to recover, the distribution of the overall time to recover is really not much longer than previous fire years, and that's because it's been of the La Nina event, essentially. The post-fire precipitation in 2020 was about 20% higher than average, and it's probably been even greater than in 2021, although that data was not fed into the model. So the burn severity effect has really been canceled out by the post-fire precipitation, so the overall time to recover might be fairly typical, or at least that's what I'm predicting with this model. So the machine learning model is not really a statistical inferential model, but it can sort of, in a speculative way, sort of suggest what's important through variable importance. And so again, we have pretty similar drivers compared to what I was showing before. This time, elevation comes out as being the, this time, the elevation is coming as important because it's pretty correlated with PET. Next, there's the NBR anomaly, the normalized burn ratio anomaly, which is closely related to the burn severity. The mean annual LAI, which is here, is again pretty much indicative of the carrying capacity. And then we have the post-fire weather, which is the precip and vapor pressure deficit anomalies, and the state of the vegetation, again, before the fire. So the 3-month LAI, probably predictive of the fuel loads, and the 12-month LAI anomaly, which maybe was predictive of whether a forest was overshooting or undershooting in the year preceding the fire. Okay, so in summary, I think what my main takeaway messages from this are is that the burn severity and the post-fire growth rate structure the time to recover. And the burn severity is perhaps not surprisingly driven by pre-fire weather and pre-existing LAI anomalies like senescence, but also maybe canopy overshoot. But perhaps most surprisingly, that the post-fire growth rate seems most strongly related to burn severity, in addition to pre-fire LAI anomalies, climate, and post-fire precipitation. And that I think this time to recover metric is predictable with fairly high accuracy using an off-the-shelf machine learning framework, and that these models really will only improve with time. So as the remote sensing record increases, we have more data to train these models, and perhaps we have more data to feed into these models. And these things could be operationalized, essentially, if they're useful, and perhaps extended to a broader suite of ecosystems. So maybe they don't just need to cover for Southeast Australia, but maybe they could cover the whole country. And finally, that I think we can use this to identify really new questions about the ecology of different forests. So when the model fails, why does it fail? Or are some ecosystems essentially just more predictable than others? And I think what this has brought in terms of new questions to my mind is, why is this post-fire growth rate higher? Why does it seem to be higher following greater burn severity? Two, what is this interplay? What does the interplay of the intermediate canopy overshoot with the short-term pre-fire leaf senescence suggest about the timing of the post-fire carbon allocation strategies? And three, Rachel brought up this question about, again, will these obligate reseeding species, will they survive given in this increasingly novel climate with an increase in fire weather, essentially? And then finally, what we really need a lot more data, especially field data, is we need to get ground level estimates of what functional groups are coming back. Are these forests, are they fundamentally different? Has grass really just come to stay? Have they invaded? And I think perhaps our remote sensing methods we can do this with, but we really need more field data to validate these things, to really better be able to upscale these. So that's all I have for you today. I think we have plenty of time for questions, no?
Thank you so much, Sami. That was fantastic. Really interesting work and very relevant to many of us. I'm gonna stop sharing so that I can see if there are any questions online in the chat. So I'll ask for questions from the room first, and then you guys online, if you can pop your questions in the chat, I think we should be able to see them. Okay. Gentleman in the back first. Did you get that question?
Sure. Yeah.
You might need to, can you say it again? For
yeah.
that?
So I think correct me if I'm wrong, but the question is about how we can use this if this method relates to the planning, the spatial planning of carbon offset programs, and species level planning. Oh yeah. Potentially, I am being filmed, and I don't really have tremendous confidence in the long-term viability of sequestering carbon in carbon offset programs, because what's already been happening, especially in the tropics, is there are RED programs that are getting hit by drought and fire, and the carbon offsets that have been sold are being respired or burnt into the atmosphere. So maybe it could be useful, but on the other hand, are carbon offsets really a viable solution? Yeah. Yeah, I think so. I think and the fire frequencies are high enough that we could probably estimate a time, a residence time of the carbon, perhaps. But yeah, I don't know. I have a lot of skepticism about carbon offset programs and their long-term usefulness in actually removing carbon from the atmosphere.
Brendan?
Good talk. I think it does a great job of kind of demonstrating these two kind of competing factors that drier, hotter weather for some periods, rainfall one. Quick recovery, you need, which of course you would expect. I was, we were just talking about this before, but I wondered in terms of the recovery, easily you can separate it down, recovery of the trees themselves, stuff coming the other story process. Do this with people, but I know that people also help in methods of separating rust.
Yeah. So yeah, there are. So I designed these two metrics of recovery in a sense to overcome the seasonal phenology of understory grasses. So this bone simple moving window approach, ostensibly, if the understory grasses are evergreen, that presents a problem. If the understory is very evergreen, that presents a problem for this method. And it also presents a problem for the logistic function as well. If the LAI algorithm can correctly estimate the LAI relative to its LAI before the fire, then perhaps it is indicating that trees are really, the evergreen trees are coming back, and that is the signal being seen. There, we did try some other methods using like spectral transforms, not spectral signature, but time series spectral transforms. Alfredo Huete's group has done a lot in this regard, trying to disentangle the seasonal grass fraction from the evergreen tree fraction. I did not have a huge amount of success with that, but it's also, there didn't really have the training data, or didn't really have the field observations to know if what that's estimating in this context, in this landscape, was accurate. So this just seems easier to defend, and it still gives us information about the recovery rate. However, yeah, that recovery rate, it's not easy to attribute it to tree or the grass or understory shrub recovery rate. I think
There's a question online.
yes, let's see. Okay, so Christine asks, can the modeling be done on finer scales, like specific fires areas? And this will be likely important if you want to associate this with field data. Yeah, I think this can totally be done on finer scales, and there's likely a broader suite of predictive information we could bring in on finer scales. So, for example, like the slope means a very different thing at a 500-meter scale than it does at a 30-meter scale, or the aspect. So I think it's entirely possible that the predictors, the static predictors at least, will likely change if we were to change the scale to reduce the spatial scale of this modeling. In terms of the more dynamic predictors, I'm not sure that I'm sure the climate variables will still come out as being the overwhelming important parts, and it might actually give better resolution about this question of burn severity and post-fire recovery rate if we were to do it at finer scales. So Yeah, I think this would be a good direction to go in, but Otis data is just very coarse and just much more computationally efficient to work with. Not to mention, I don't think there are any fine scale LAI products out there, but that doesn't mean that this couldn't be done with, say, a different vegetation index. Kate Fuller asks, very high severity may indicate total removal of the canopy. Do you expect that the rapid recovery high severity relationship is related to this? Perhaps these high severity sites have been knocked back to an earlier successional stage, which would explain the rapid production of LAI. This is probably similar to the previous question. Yeah, I do not know. Again, don't really have field observations to know if these areas that had like what appeared to be complete consumption, if the recovery is from epicormic resprouting, or if it's because of some sort of sustained colonization by new growth, understory growth, etc. So this is yeah, if anything, this is an argument that really need more field data to put any of these remote sensing things into context.
Which is, of course, what we want to hear. So thank you, Sami. I do have a question as well, which is you've quantified time to recovery, but that assumes that everything did actually recover. Did any pixels come out as not actually recovering, or does it always come back?
Yeah, so even good question. So even with this fairly generous window of recovery, yeah, essentially 3% of pixels during this time frame did not recover. They didn't reach this quarter unit standard deviation threshold. So in those pixels, like even after the longest times to recover were essentially as long as the remote sensing record. So we couldn't, and this is important because we couldn't really use the most recent 5-6 years of data because it's not enough time to really estimate the time to recover. Yeah, so I think despite what I was saying, 97% of the area seems to have recovered. There's definitely some areas that maybe they didn't recover or they transitioned into something else. So.
Alison?
Yeah, so I just focused on three classes. So eucalypt open forests, eucalypt tall open forests, and eucalypt woodlands. And of course, the NVIS classification is probably far from perfect as well. But just yeah, vegetation types under those three classifications. Overall, no. Well, I mean, but a lot of that is sort of it's encoded in the climate context. So the highest end of the PET spectrum is pretty much always going to be in these eucalypt open woodlands. And then for these two, it's just sort of a mixture along the more coastal regions, but yeah, I mean, largely. So there are like 3% of the pixels did not recover. No, not off the top of my head. That's a good point though. I should go look what those pixels were.
I think that would be a really useful number to have for your fingertips.
Yeah.
Because I can see a lot of people ask that question.
Yeah. Well, yeah, exactly. So I think we can use this method to ask, like, why does the model fail, or why do we have these deviations from unexpected behavior? Oh, yeah. Yeah, no, it's good. I didn't mention, but yeah, there are a number of studies also doing like litter fall traps that have also sort of quantified that in the time scale of 3 to 10 years, the litter fall rates have recovered. So which would correspond with our canopy recovery, although that's really interesting. I have to ask you more about this LiDAR time to recover.
Sami, can you just check the chat? Is there any
Yeah.
other questions in the chat?
So I think that's it.
Okay, all right. In that case, so thank you again, Sami, for a really, really interesting and thought-provoking seminar that I'm sure we will chat to you more about in time to come. So thanks, Sami.
Thank you all for having me. Should I end the? Okay.